Hi, I'm Brian Creer, tutoring high school physics. Today's topic, relativity. So two main things you should know about relativity. First off, the laws of physics are constant for all inertial reference frames. What's an inertial reference frame? It's just a thing where everything inside of it is moving at the same speed. So for instance, Earth. Everything on Earth is moving at the same speed, which is Earth's rotation around its axis. So let me give you another inertial reference frame. Let's say a train. Everything there is going to be moving at the speed of the train. Let's say that's 40 meters per second. So the laws of physics are going to be constant in there, and they're going to be the same as outside of it. So if you're anywhere on the Earth and you drop a teacup, it's going to fall straight down with the acceleration due to gravity. If you're standing on the train and you drop the same teacup, you'll see it go straight down with the acceleration due to gravity. But let's say that you're between inertial reference frames. Let's say that you have an observer standing on the Earth and he's watching somebody on the train drop the teacup. Well, he's also going to see the acceleration due to gravity straight down, but he will also see the teacup move with the speed of the train at 40 meters per second. So this tricky space between inertial reference frames that relativity deals with. Okay, so let's move on. Second, the speed of light in a vacuum is always 3 times 10 to the 8th meters per second. So what does this mean? Well, if you're on the Earth and you shine light, you're going to see it move at 3 times 10 to the 8th meters per second. But let's say that you're on the train and you shine light. Well, you'll see it move at 3 times 10 to the 8th meters per second. What will somebody outside the train see? Well, typically, you would expect him to see the speed of light plus the speed of the train. But that's not actually true. He'll only see 3 times 10 to the 8th meters per second. He will not add on the speed of the train. That's pretty crazy. Light is not affected by any other speed. There's nothing that goes faster than the speed of light, at least to our knowledge so far. So to calculate the speed of something, we use this equation. Well, typically we'll only use that equation for speeds that are close to the speed of light, because if we have small speeds that are, like regular everyday speeds, this denominator will just become 1, and we could use regular Newtonian physics for it. But for things near the speed of light, we use this equation. So u is going to be the speed of the reference frame, and v is going to be the speed that's measured inside that reference frame. And we're going to calculate the speed seen by an observer outside of the reference frame. So let's get to work. Let's say we have a spaceship moving at 4/5 the speed of light, and we see an object inside the spaceship that we measured 2/5 the speed of light. The outside observer does not see 6/5 the speed of light. Let's find out what they see. So we have 4/5 c plus 2/5 c divided by 1 plus, we're going to multiply those two things together, 2/5 c divided by c squared. Okay, so 4/5 c plus 2/5 c is 6/5 c. That's pretty easy. 4/5 c times 2/5 c is going to give us 16 over 25 c squared, but it's going to cancel out with the denominator of c squared. So we're just going to end up with, sorry, not 16 over 25, 8 over 25. And so then we add in the denominator, and we go through the division. If you go through all the division, punch out in your calculator, you'll end up with the observed velocity at 30 over 33 the speed of light. So very close to the speed of light, but not quite, and certainly not over the speed of light. Okay. So that should have blown your mind. If not, let me blow your mind. Time is different between inertial reference frames. So the time observed is equivalent to gamma, this thing over here, which we're going to use again later, times the time that we observe within the reference frame. So let's say that we're in a reference frame and we observe 5 seconds. And actually, let's say that we're on a spaceship at 4/5 the speed of light. So what is an observer going to experience in terms of time? Well, delta t sub 2 is equivalent to gamma, so that's the square root of 1 over 1 minus the speed of the reference frame, which is going to be 4/5 c, and we're going to divide that by the speed of light, so the c's just cancel out, and we have 4/5 squared times 5 seconds. Okay, let's start working this out. 4/5 squared is going to be 16 over 25. 1 minus 16 over 25 is going to be 9 over 25. And we're going to flip that over because it's 1 over that. You get the square root of 25 over 9. A lot of math in there, but punch into your calculator if you want to check. 5 seconds, and the square root of 25 over 9 is 5/3, and 5/3 times 5 seconds is about 8 seconds. We experience 5 seconds inside of our spaceship, but somebody outside is going to experience a whole 8 seconds go by. Imagine applying this to much longer time, say years even. So there's going to be a big difference over that. So that's time dilation. Time is different between inertial reference frames. And if your mind still isn't blown, so is length. So the observed length is equivalent to the length that we're observing inside the reference frame divided by gamma. So let's say we've got a length of 5 meters observed inside our inertial reference frame. Let's get to work. So length 2 is equivalent to 5 meters divided by the square root of 1 over 1 minus our spaceship, let's say 4/5 c, so it's just going to be 4/5. It's going to be squared. So we've already worked out our particular gamma. It's the square root of 25 over 9, which is just going to be 5 over 3. But we're dividing by 5 over 3, so it's in fact 5 meters times 3 over 5, L2 equals. And so the 5s are just going to cancel out. We're going to get an observed length of 3 meters. So if we have a 5-meter object inside our spaceship, it's going to appear shorter to an outside observer, a whole 2 meters shorter. So again, pretty crazy things happening. Okay, to recap, the laws of physics are constant for all inertial reference frames. An inertial reference frame is just something where everyone's moving at the same speed, like the Earth or a train. The speed of light in a vacuum is always 3 times 10 to the 8th meters per second. Nothing goes faster than that to our knowledge. So to calculate the speed of something moving close to the speed of light within inertial reference frame, we have the equation that the observed speed is equivalent to u, which is the speed of the reference frame, plus v, which is the speed measured inside that frame, divided by 1 plus the quantity of u times v divided by c squared. Time is also different between inertial reference frames. The time observed by an outside observer is equivalent to gamma, which is square root of 1 divided by 1 minus the quantity of the speed of the reference frame divided by the speed of light squared, so that's written down here, times the speed that is measured inside the reference frame. Length is also relative, so it's different between reference frames. The length observed is equivalent to length observed inside the reference frame divided by gamma. Alright, that's all for now. Again, I'm Brian Preer. See you next time.